In this lecture, we're going to look at consumer demand theory, which is perhaps the most exciting theory at the undergraduate level, at least in microeconomics. One of the reasons for that is that it relies on the concept of utility, and because it does that, consumer demand theory can also be used in environmental economics. Indeed, it's the foundation of environmental non-market valuation, valuing things that don't get exchanged in the marketplace. In fact, one of the authors that we look at, Robert Nelson, has argued that the whole environmental movement has been taken over by economists because of this particular theory. When it comes to managerial economics and business students, I don't think that this theory is of much use to them. Well, it can be in some ways, and you need to have some understanding of it. But I think all of the consumer demand theory here can be boiled down to the last slide that I'm going to talk about in this particular lecture. Consumer demand theory borrows from production theory. In fact, the mathematics is pretty well the same, as we will see. In production theory, we had three methods of approaching our problem. One was to maximize output subject to a cost constraint. The second was simply to minimize cost subject to a particular level of output. And the third was to maximize profit. In the case of consumer demand theory, we do not have that third case of trying to maximize our utility or some kind of profit related to utility, because that doesn't exist. So here, the first problem, which we refer to as the primal problem, is output maximization, where we maximize quantity, output, subject to a constraint. Suppose that the cost constraint, which is given by this line, these lines here, all right, and what we seek to do is find the highest quantity of output given a particular constraint. So these isoquants tell us how much output there is. And then if our cost constraint is given by this yellow cost, then we would end up at this yellow place here. If the cost instead was at C1, which now becomes our C0 in this particular problem, we find that this is the point on the expansion path to which we go. Now, the dual problem in production theory is one of cost minimization. So here what we do is we want to find the minimum cost associated with achieving a particular level of output given by Q0. Again, that's an isoquant. Again, remember the slope of the cost constraint is given by the ratio of the prices, in this case the wage rate over the rental rate of capital, and we have the negative because that line slopes down, and it has to equal the slope of the isoquant, which is given by the marginal rate of technical substitution, which is the negative of the change in capital, the rise, over the change in labor, the run, which turns out to be equal to the marginal product of labor over the marginal product of capital. In the case of consumer demand theory, we wish to minimize the budget required to achieve a particular level of utility. So in the previous problem, if we were to bring that into the consumer demand framework, then we would maximize utility subject to a budget constraint. So what we have instead in consumer demand theory, instead of these isoquants, we make these indifference curves. Instead of the cost constraint, we have a budget constraint, which looks exactly like this, where now the slope of the budget constraint is equal to the minus the price of quantity 1 over the price of quantity 2, and it has to equal the slope of the indifference curve now, which we call the marginal rate of substitution rather than the marginal rate of technical substitution, which would then be given by the minus of what is on the the vertical axis, in other words, delta Q2 over delta Q1, and that would equal to the marginal product of the marginal utility of 1 divided by the marginal utility of 2. So let's go a little bit further into this. So let's start by looking at indifference curves. So here we have two outputs or two consumer goods, Q1 and Q2, and we have these indifference curves. And they tell us what the level of utility is as we get an increase in the purchases of Q1 and Q2. Notice that there's a substitution implicit here between Q1 and Q2. So in other words, if we wanted to be on utility level 25, then we could take a reduction in Q1 and it has to be substituted for or compensated for by increases in Q2. Now notice that these indifference curves I've got labeled as 12, 25, 75, but I could just as well label them 1, 2, and 3 because the indifference curves are not always needing to be what we call cardinal. They're ordinal. In other words, they basically rank things. They're a ranking, nothing more. If they actually had numbers to them, so I've got numbers here. With numbers, these things become cardinal, but if they are referring only to a ranking and it doesn't matter what the numbers are that I assign to them, as long as they increase as I move in this direction, then I'm fine, and I refer to these as ordinal. So we can specify a utility function as follows, and notice that this specification is exactly what we had in production theory when we talked about a Cobb-Douglas production function. This is basically a quadratic in logs. So combinations of Q1 and Q2 are needed to produce the same level of utility. And we notice here the similarity between isoquants and indifference curves and between consumer demand theory and the theory of the firm. And as I noted, the main difference is simply the difference relating to the measurement. We can measure output, but we cannot measure utility except in some sense that people prefer A to B. All right, we can't attach a utility to how much they prefer A to B. So if Q1 is some good, such as recreation goods, and Q2 refers to all goods except Q1, we find that the indifference curves must intersect the vertical axes. Now, why would that be the case? Well, clearly because I can do away with all the recreation, but I can't do away with all the other goods that I need to live. So let's look at ordinary demand, or what we call Marshallian demand. Here we want to maximize utility from two goods, the good in question, Q, and Qn here refers to all other goods, And our budget constraint, we refer to the budget level as M, so you have a budget given M, and that's equal to the price of the good that we're looking at plus the price of all other goods times the amount of those goods that are consumed. So very much like we had the cost constraint, R times K plus wage times labor, we have price of Q1 times Q, price of all the other goods times the amount of all the other goods that are consumed. That's our budget constraint. Now for ease of working, we just assume that Pn is equal to 1, so everything else is also measured in a kind of a dollars term. And we refer to this as the primal problem. Okay, we can look at the derivation of an ordinary, or sometimes called Marshallian demand curve, where what we're doing is we're maximizing utility subject to a budget constraint. So the budget constraint is given here by a budget limit of M0, and given that Qn, the price of Qn is 1, and the price of Q is P0, then what we do is we divide the budget, M0, by P0, and that gives us the maximum amount of Q that we could purchase. On the other hand, if we don't buy any Q, the maximum amount of Qn we can purchase is given by M0 divided by the price of Qn, and that is 1, so M0. We then take the indifference curve for utility level, in this case U0, that is tangent to this budget constraint. And remember, this budget constraint, you can see what the slope is by taking the rise, which is from 0 to M0. The rise is negative M0, and the run is m0 over p0, so rise over run is negative m0 divided by m0 p0, so the equation or the slope is given by negative p0. I just haven't put the negative right there. Now don't let this more complicated diagram throw you off. Again, we have that m0 is our budget constraint, and here again is that m0 divided by p0 is your maximum amount of Q you could buy, with p0 being the price of Q. Now if the price of Q was less and it was p2, then the amount of Q we can buy, remember if p2 is less than p0, you can buy more p2, and that would be given over here. And if the price were higher than p0, namely p1, then we would get the amount that you could buy here is Q divided by p1, which is the slope of this line here. So we begin by taking the budget line for m0 given p0, so this is then the slope, the negative p0, and we're at utility level u0. If we increase the price, then we end up with this dotted budget constraint, and we end up at point X. If we reduce the price to P2, then we end up at Y on a higher indifference curve. So we kept budget constant, but we allowed utility to vary. So now, this more complicated diagram is not that complicated. This upper part is what you saw on the previous slide, and all we've done is we've taken these values of Qx and we've matched them to these prices. All right, remember the price P1 is the higher price, P0 is our starting price, and then we have Qy is the lower price, P2, and we can just plot down here P2, Qy, P0, 0, or Q0, and then P1 matches this Q of X. And this dotted line then is our Marshallian demand function. Now, it's a function of price, here's the price, but it's also a function of the level of the budget, M. So as the budget increases, then that line would shift. Okay, if the budget, it would shift out. If the budget were to be reduced in M, in other words, M is reduced, it would shift in. So notice that this demand for Q is a function of its own price, P, the price of Qn, and income, M. All right, so we can write that as Qm equals the M referring to Marshallian or ordinary demand function is a function of price, price of other goods, and M. So now we can look at and determine what we call a compensated demand function. So here, this is the dual problem. The problem that we previously looked at was the primal problem. So here what we want to do is minimize the budget, M. So we want to minimize the amount that we pay for the goods and services that we purchase, subject to a given level of utility. And again, we're going to let this big P now equal little p equal the price of good Q over the price of Qn. So here we have exactly the same diagram that we had previously to start our derivation of the ordinary or Marshallian demand function. Here we're going to look at the derivation of the compensated, or sometimes it's referred to as the Hicksian demand function. So here was our starting point where we had this budget M0 and this price P0, and everything's the same here. We got the same place where the U0 is tangent to the budget line, but now we're going to change it a little bit. Rather than shifting the utility function, in other words, allowing utility to change as we change prices, we're now going to change prices again like we did before. So these slopes of the lines are going to change, except that we're going to stay tangent to this utility, this indifference function given by the utility function u0 or utility level u0. Now notice what has happened is now instead of having this dotted line originating here at m0 and then coming down like this, we have had that line there, but now we're going to compensate because this is a higher price. P1 is a higher price than P0. So if we were to draw that dotted line, that dashed line here, then we would end up at a lower level of indifference like we did in the previous diagrams. But now we're going to shift that line to the right until it's tangent to U0, and that occurs at point 1. And this difference between M1 and M0 is the amount that we have to compensate the person in order to be able to get to the same level of indifference, the same utility, to get the same utility. Now if the price were to drop, so in other words P2 is less than P0, then instead of having that line follow along like this and enabling us to get to a higher level of indifference, a higher utility level, we're going to take away income from the individual so that they can only get to point 2 where the tangency occurs between the indifference function represented by U0 and the new budget constraint M2. Now in this case, M0 to M2 represents the amount that the consumer must give back in order to get to P2. In other words, it's the amount that the consumer would be willing to pay for a reduction in the price of that particular good Q. Now notice that in this case utility is kept constant, but the budget varies. Now again we can draw a demand curve as we did before, and again M1 is here given by 1. We can follow that all the way down to this P1, and then from 0 we have the P0, and then from 2 we have the P2, and we can plot the line that's associated with that, and that's the demand Hicksian or compensated, and it's a function of price, what's on this axis, and utility, and it's utility that changes. If utility is higher, then it shifts that line to the right. If it's lower, it shifts the line to the left. Now consider that here we've had this function here where Q is a function of price, quantity, and utility. The other one had ordinary demand, Qm is a function of price, Qn, the price of Qn, and M. All right, now if you were to run a regression, you'd look at the price of Qn. You could have that available. You could get the price of this particular good, but you can't get utility, but you can get budget. So it's much easier to estimate a Marshallian demand as opposed to a Hicksian demand function. So the consumer problem can be summarized in 2 ways. One, the primal problem is to maximize utility of 2 goods, Q1 and Q2. We want to maximize the utility or level of satisfaction subject to this budget constraint where M0 is the given budget. The dual problem then is to minimize the budget or expenditure required to achieve a particular level of satisfaction or utility. Utility functions take on functional forms much like those of production functions. They're very similar, and I showed that at the beginning of the lecture where utility was expressed as a Cobb-Douglas production function, or the same functional form rather. Solving either one of the above constrained optimization problems, so you could solve either the primal problem or the dual problem, leads to a demand function. But these demand functions differ. But however, there's something called a Roy's identity and a Hotelling lemma that enable you to switch. So in other words, if I solve the dual problem, I can then use the results of one of these theorems in calculus to recover the ordinary demand function. So in other words, if I figure out what the compensated demand function is, then I can figure out what the ordinary demand function is on the basis of that. Or I can find the ordinary demand function and then somehow convert that back into finding the compensated demand function. That's what gets into the heavy mathematics and the interesting part of consumer demand theory. So if we look at the two together, and this is an even more complicated problem or diagram, notice that I'm having some problems here with the subscript should be on that P. But what we have is an ordinary demand function where we allow this dotted line to change to remain constant. In other words, it originates out of M0 as we change price, or the compensated demand function where it shifts either to the right or to the left in order to retain this utility at U0. And we can then plot these two functions, and we notice that the compensated demand function, which allows this utility to change, is steeper than the ordinary demand function. And we can go a little bit further. So we can put the Hicksian or compensated demand functions together on the same diagram as the ordinary or Marshallian demand function. And we notice that along this red line, which represents our ordinary or Marshallian demand function, what changes? The thing that changes is not our budget, but rather the utility levels. The Hicksian demand function, what changes is not our utility levels, but our budget. Now we jump from this black line to this dotted or dashed brown line simply because along that ordinary demand function, what has changed is the utility level. So here the utility level is lower, and here the utility level is higher. And think about it, you've got a higher price here, so you're going to get less utility because you can't buy the same number of goods. Here you've got a lower price, you can buy more goods, and your utility level is higher as a result. Now there's one other interesting thing that comes to play here, and that is the question about cost of living allowance clauses, these COLA clauses in union contracts or in defined benefit pension plans. Do they provide the correct amount of compensation? That has been an issue that theory can resolve. Assume that the price increases from P0 to P1 in this particular diagram. All right, so here P0, and we get an increase to P1, which would then take us to a lower level of utility. So here we've got a starting point 0, and if the price increases, we'd end up there. So this is a case where inflation hurts people on a fixed income. The fixed income would be represented by this M0 or E0, where E refers to the expenditure level that's required. Now, if you're being compensated, how does this compensation work? Well, if you're compensated so that you achieve the same level of utility, the same satisfaction as you did before, you'd want to be compensated to U0, and you'd end up at K, all right, and your budget would then increase from E0 to EK, your expenditure that is, to retain utility level U0. However, you can't measure U0. You don't know where it is. You don't know where it lies. So instead, the compensation occurs at 0, where the amount of Q1 and the amount of Q2, the basket of goods that you buy, remains the same. So the compensation allows you to buy the same basket of goods as previously. But what does that do? Given this change in prices, given that the relative prices of Q1 has increased relative to that of other goods, this compensation would then enable you to get to a higher level of utility, U1, a higher indifference curve, at point R. So what happens is the overall compensation isn't case of overcompensation. And that is given by this difference ER, expenditure level to achieve R, versus the expenditure level to achieve K. Expenditure level ER allows you to get to 0, but you don't go there because the relative prices have changed. Instead, you go to R. So Hicksian compensation, EK minus M0 or E0, enables an individual to attain the same level of utility as previously. Slutsky compensation, ER minus M0, enables individuals to consume the same bundle of goods, 0.0, as previously, but the individual will increase utility by moving from 0.0 to R. In this slide, we put the compensated or Hicksian demand function along with the Slutsky compensation demand function, where the compensation is to the previous basket of goods, and the ordinary demand function all on one graph, and all of them intersecting at this particular point. So now we come to supply and demand. Having determined the theory underlying both consumer demand functions, and from our analysis of the firm, we can look at the market where both firms and consumers operate. The market consists of demand and a supply function, and where the two intersect, and sometimes that is a free market, sometimes it's not, but that determines at the point where prices and quantities are determined, the point of intersection. In economics, we employ abductive reasoning, and the reason for that is that our deductive reasoning, based on what we've done in this particular lecture, leads to demand functions that are never linear. In fact, the types of demand functions that fall out of the theory tend to be very complicated and often of a functional form that is impossible or nearly impossible to estimate using data from the real world. So instead, economists tend to represent these demand functions by linear supply and linear demand. This, despite the fact that one cannot derive a linear demand function or even a system of linear demand functions from any utility function that satisfies the properties required of a utility function, such as, for example, transitivity and diminishing marginal utility. But of course, this issue is not of interest to managerial economists or business students, but it is of interest to anyone working in the theory of economics or an economics period. So we come to this last slide, where the sum of individuals' ordinary demand functions, the sum of their individual Marshallian demand functions, constitutes the market demand, which represents, and this is really important, the maximum willingness of individuals to pay for a good or service. Now, the demand function is a marginal benefit, a marginal willingness to pay. All right, marginal benefit or marginal willingness to pay. So that means that the area underneath any marginal curve refers to the total benefit, the total. So the area under the demand function and above the price therefore constitutes consumer surplus. This is our consumer surplus, because a consumer would be, some consumers would be willing to pay, say, this amount for this good, or rather the market would have consumers, a number of consumers who would be willing to pay this price up here, all right, for this amount of goods. They'd be willing to pay that or more. So we come to here, where the number of consumers willing to pay this price P star or a higher price would clear the market at Q star. So then, because they're not paying the higher price, but rather P star, anything between the price they're willing to pay and P star constitutes a consumer surplus. Likewise, we've already talked about quasi-rent, which is equal to producer surplus. This is the producer surplus because this supply curve represents the marginal cost, and anything below the supply curve is your total cost. So your total cost of production is this area that I'm outlining here. But the benefit that the producer gets is given by this bigger area, which is equal to the price times the amount sold, P star Q star, and this difference between that box here and this area here is the producer surplus. And that's really all you need to know in terms of these kind of models.